Good night, everyone, and welcome back to Fundamentals of Engineering with Farhad. Mechanics of Materials, Solution 3 of a two simple supported beam handling a distributed load for maximum deflection calculation. We have solved this example so far with two integration method, integration from load function to get the deflection, maximum deflection at its center, and also with the help of solution to determination of elastic curve based off moment equation. So far we solved the solution one, elastic curve from load, distributed load, load distribution function, and also elastic curve from moment function. The solution 2 was a bit easier than solution 1, and solution 3, which is the today's work, is moment area method and is far simpler than last two, much simpler and much faster than last two um, approaches. And finally, in the other video, in the next video, we'll solve it with the combined method. We focus on the moment area method for now. So if we have a two simple support beam A, B handling a distributed load of W, we want to solve it with moment area method. So our solution 3 is moment area method. Based off the name of the method, we simply know we need the moment diagram. So if a load of W apply distributed load of W apply entire all along the entire span, half of the load goes for support A, that's WL over 2, and the other half at R sub B, which is WL over 2. If we draw the shear diagram, it's become a linear shear diagram. So we have a linear shear diagram which start at the amount of, it just moves up by the amount of R sub A, that's WL over 2, and it's reach to 0 at center, move all the way down to negative WL over 2, and by the help of WL over 2 RB just come back to 0. And if we draw the moment diagram, that's a second degree equation, and the maximum moment happens at its center due to the symmetry, and that's the area under this triangle. Area under shear is the amount of maximum moment, M max. So the numeric value for that, that's a, if this is L over 2, the area of this triangle is a half of WL over 2 times L over 2, and it just gives us WL square over 8. And if you divide it by EI for calculation of deflection, it just gives you WL over 2 over 8 EI. So far we draw the moment, shear and moment diagram, and then delta maximum in the moment area approach is, if you draw the approximate deflected shape of the beam, you can easily see this is delta maximum, and that's simply equal to tangential deviation of A with respect to C. So if we call C, this is center, stands for C, and this is T A with respect to C. Tangential deviation of A, a vertical line from A, and a horizontal line passing through the C. This is deflected beam, and this is C center. So TA over C, and base of second moment area theorem, tangential deviation of A with respect to C is nothing but area under M over EI times the X bar, and X bar is calculated from the first point, which is A here, from vertical line. So if this is our case, we need to calculate, and definitely you can see delta maximum is exactly like the TA over C. So we are looking for X bar to do this mass. So if we draw a vertical line here, we can easily see the top part is a second degree, because this is second degree curve, and this is a spandrel. It just gives us, wow, this is a parabolic spandrel with the equation of y is equal to k times x squared. We uh, we have talked about the general spandrel, parabolic spandrel, cubic spandrel in previous video, which I will provide you the link in the comment as well as at the end of this video. So if we know the top part is a parabolic spandrel and we subtract it from the rectangle, we can easily get first get the area of this part, which is our area, and then the centroid of this area, which we are looking for in our moment area method. That's the only thing we need in our geometry calculation for moment area. So if you remember, for centroid calculation for such a thing, we had it like x bar. X bar is the centroid for this part, and that's 5 over 8 times b, and b is the length of our rectangle. So if that's the case, we apply the same thing to our calculation. So delta maximum is TA with respect to C. Delta maximum is equal to T tangential deviation of A with respect to C, and that's equal to M over EI times X bar. For X bar, if we just apply the previous note from what we were talking about, X bar is 5/8 over B, which is L over 2 for our case. So we get the centroid of our shape, and that's simply we can jot down the delta maximum, which is the area under M over EI for this bluish area. And if you subtract the area of a parabolic spandrel, which is 1/3 of BH or LH, it just says that's 2/3 of WL squared over 8 EI. We need an EI here, times L over 2, because this distance is L over 2, times the centroid, which is here 5 over 8 L over 2, and the first part is M over EI, and the second part is X bar. If you have all of them and you calculate the numeric value of that, that's a numerical parametric. Delta max is equal to 5WL to the fourth over 384 EI. That's what we were looking for, and you can see it's much simpler if you just work around a bit with the geometry and ignore in the integration method. We have to integrate the load for consecutive integration. In moment, we have to cut the beam through, get the moment equation and integrate it twice. But in geometric method, we just need to jot down this part, but you have to be careful to calculate the area and also the centroid of this part. That's all you need to do. And also theta A over C, we definitely know theta C is a center. There is no slope. It's just 0. Theta C is equal to 0. So theta A over C is M over EI, and that's equal to theta at A. If we want to calculate the angle of bending or rotation at A or B, they are identical to each other. If you remember from the other methods, we get it like WL cubed over 24 EI. If you do the mass, theta A over C is the area, of this part, and that's nothing but 2/3 of WL squared over 8 EI times L over 2. This length is L over 2. Mhm. So our theta A with respect to C, or theta A is equal to, that's equal also to theta A, and that's also equal to theta B. That's WL cubed over 24 EI. So again, our delta maximum for a two simple supported beam with distributed load of W is 5 WL to the fourth over 384 EI, and theta A equal to theta B, that's WL cubed over 24 EI. And definitely this is our delta max. Thank you. We'll solve this problem with our last method, which is the combined method, which is even the interesting part is even the combined method. I do believe it's even simpler than, it's faster and simpler than the solution tree even moment area method. Thank you.